In chemistry, one of the first major hurdles is learning that a process called reduction actually means gaining something. It feels backward, but oxidation and reduction never happen in isolation. If one atom loses something in a reaction, another atom must gain it. To map exactly what is being lost and gained, we look at these reactions through three distinct lenses: oxygen, electrons, and oxidation numbers. This first column is the simplest. In this dimension, oxidation is the gain of oxygen, and reduction is the loss of oxygen. That definition works well if oxygen is present in the reaction, but many chemical equations don't involve oxygen at all, which makes the next two dimensions critical for exam success. The terminology makes sense once you consider the charge. Electrons are negatively charged particles, so when an atom gains one, its overall electrical charge is mathematically reduced. The standard way to track this movement is the mnemonic OIL RIG. Oxidation is loss of electrons, reduction is gain of electrons. Once you know what's happening to the electrons, you can identify the chemical agents. Think of an agent as a middleman who causes an action to happen to someone else. An oxidizing agent causes another atom to oxidize. To do that, the agent has to steal an electron from that atom. Because the agent gains that negative electron, the oxidizing agent itself is reduced. You always define an agent strictly by what it does to the other reactant, never by what happens to the agent itself. The third and most precise dimension uses formal oxidation numbers. This method tracks specific bookkeeping rules to analyze reactions where electron transfers aren't immediately visible. There are two core rules to apply here. First, elements in their natural, uncombined state always have an oxidation number of exactly 0. Second, the sum of all oxidation numbers within a neutral compound must balance out to 0. Let's test these rules on a standard IGCSE exam equation. Copper 2 oxide reacts to form copper 1 oxide plus oxygen gas. Try to calculate the starting and ending oxidation numbers for both copper and oxygen. Pause the video here and give it a shot. Tracking these specific numerical changes across an equation is the most reliable way to prove a reaction is redox on an exam. On the left side, we start with our known value. Oxygen has an oxidation state of -2. To balance the compound to 0, this copper must be +2. On the right, the first product is Cu2O. The oxygen is still -2, but because there are now 2 copper atoms, each one only needs a +1 charge to reach 0. Finally, we look at the oxygen gas. Since it is an uncombined element, its oxidation number is 0. Copper drops from +2 to +1, so it has been reduced. Oxygen moves from -2 up to 0, so it has been oxidized. This grid summarizes the entire framework. You can prove oxidation by a gain in oxygen, a loss of electrons, or an increase in oxidation number. Reduction is the inverse. Internalizing this three-dimensional framework provides a consistent, objective checklist. It ensures every reaction is judged by measurable changes in oxygen, electrons, or oxidation states. To practice identifying these agents and calculating oxidation states yourself, head over to studybuddy.tech to run through our diagnostic tools.